This is an interactive tutorial. So I want you all to be staring at your laptop screens the whole time. Okay, so if you find my presentation in the agenda, it will give you a link to a GitHub over here at PESC 2019. And if you scroll down to AE and GAN, in here there are two Jupyter notebooks that we're going to use. So who's familiar with Jupyter? Great. Who's familiar with Google Colab? Okay, if you're not, that's okay. It's really easy. So copy this GitHub link and then go to colab.research.google.com. And you should get a site that looks like this. Google has online Jupyter Notebook execution available. So if you want to run these notebooks on your laptop, that's totally fine. There's some software you'll need. You'll need things like NumPy, TensorFlow, Matplotlib. If you don't have that, come to Colab, go over to the GitHub tab, paste that GitHub link that you copied and hit enter, and it will, oops, it should load all of your notebooks that it finds in this repository. Good. Did anyone else succeed with this?
Yes.
You guys did? Okay. Well, that's fine. I'm going to move on because I already have them loaded. Okay. So let's talk about the subject for this session. Who has seen the fake celebrity photos where an artificial intelligence model has made an image of a celebrity that looks lifelike and it's a person that does not exist? Who's seen those? Okay, so in the next 45 minutes and 56 seconds, we're going to learn how to do that. We're going to do this in two steps. We're going to talk about autoencoders, and we're going to talk about generative adversarial models. And unfortunately, in the 40 minutes we have, you don't have enough time to train a network to do this for celebrity photos, so we're going to do it with the MNIST handwritten digit data set. So come over to this Autoencoders Jupyter notebook, and this is the one we're going to start with. So you may be familiar with a classical technique called principal component analysis, where you take a big data set of points in some space, and you find all of the principal components of it, and you can use this as a way to reduce your data set because you find the right eigenvalues and eigenvectors that represent this data set, and you can throw away the most insignificant ones. This is kind of a data compression technique. That is a linear technique where you're just mapping it onto a new coordinate system, in effect. With deep learning and neural networks in general, you can do a similar technique in a nonlinear fashion. As Prasanna mentioned, the introduction of nonlinear activations in your neural networks offers you a lot of opportunities to take classical techniques and make them nonlinear and really extend their reach to new, more complex data sets. So autoencoders is the way we do this. It's conceptually a pretty simple model. So you take a neural network that takes an input data set. Here we're going to use images. And you just apply transformations to the images, and you get it down to a small subset of the data. So you can, in this one, we're going to take images that are 28 by 28 pixels and map them down to just 20 floating point numbers. So that's a compression of about 20, 30 times the data size. And there's another step, a decoder, whose job is to take that compressed data and explode it back up to the original image. So you've basically forced your neural network to take your data and shove it through a tiny pipe where you get just a little bit of information preserved. And the idea is you're forcing your network to learn what's the most important features of these images and how can I reconstruct the original image from them. So let's get started. I want you to go through this tutorial network with me, and I'll walk you through all the steps as we build these networks and train them. So you should be able to load all of the includes, and if you don't, raise your hand and I'll volunteer Prasanna to run around and help everyone. Good, so 2 people couldn't load it. And then this is the data set that we're going to use this MNIST data set. By the way, who's familiar with TensorFlow? Good. Okay. I saw a question.
So what was the site again for the
If you find my slides in the AppEsk, there's the Colab site, colab.research.google.com, I believe. Just Google Colab, and it should come up.
So if you go to the GitHub link, there's a README, and in the README there is a direct link.
Oh yeah.
Okay.
Excellent. Thank you.
That orange thing doesn't appear on mine. That orange thing doesn't appear.
Okay.
File open.
So sounds like you go to File, Open Notebook. Great. Okay, so we're going to use TensorFlow for these models. And I import all my requirements, TensorFlow, NumPy. I have a random number generator. And I get the data set from MNIST. And one of the cool things about this particular autoencoder is it's just going to learn all of the MNIST images and how to compress them and decompress them. You don't care about the labels. So you can basically throw away the labels for the data for this example. Who's familiar with the residual network concept? Great. So you learned about neural networks in the previous talk. There's a follow-up to those called convolutional neural networks, where instead of taking big, long feature vectors and doing a weight for every component that goes into one output, and then you repeat down the line, there's a convolutional version, which is a much smaller network. You just apply some moving window of features across your image, and that becomes your output image. There's an extension to that called residual networks, and you can search for these. This won the ImageNet competition when it arrived and was kind of a milestone in deep learning research. But the basic building block of a residual network is called this residual block. So it's two convolutional layers with some batch normalization layers. And what I mean by this is, if you're not familiar with batch normalization, this is a way to keep your images fairly consistent throughout the training data set. If you imagine a situation where you're training cats versus dogs, as per the usual example, and you have a really dark image of a cat and a really bright image of a cat, for us, we can tell that's still a cat. We're used to that dark-light difference, but a neural network doesn't understand intuitively that the important features aren't the relative brightness of the image, but the presence of a cat. So there are these batch normalization layers that will take your images and normalize them to some mean normalization that it's learning from your data set during training time. And every image that comes in, it will normalize it to that so that your network is focusing on the features that are important and not the overall normalization. So this residual block just takes your input. It goes through a convolution, a batch normalization, a nonlinear activation, and then another layer of convolution, batch normalization. And then you add your original input to all of that, and you do an activation. And the advantage of this is Prasanna alluded to a vanishing gradients problem in his previous talk at the end during the questions. And because of this shortcut connection where you're doing this sum, there's a direct path for your gradients from your loss function all the way back through your network. So using these techniques, you can train really big, really deep networks very well. You have a lot less problems with vanishing gradients, and you get much better convergence. So we're going to use this technique. I'm doing this with Keras, so this inherits from a Keras model, and by hitting Shift-Enter to evaluate this, you've basically defined this as another Keras-type layer in your notebook. So here's my encoder. This is the network that's going to take an input image and encode it down to a small latent size vector. I've set a latent size here of 10. You're welcome to configure this when you create the network. And I allow you to change the activation function too if you want to play with different nonlinear activations. If you want to try a linear activation and make this a linear convolutional neural network, you can set this to tf.identity and see if that still gives you the good results or you're stuck in something that can't learn what it needs to learn. This network is fairly simple. It's a few convolutional layers, this res block, and then pooling, another residual block, pooling, another residual block, pooling. So it's 3 residual blocks deep, 3 pooling layers. Each time there's a pooling layer, it will compress the size of the image, so it goes from 28 to 14 to 7 to, I believe, 3. And then there's a dense network that will just take that final 3x3 image and map it to a 10-long feature vector. And this is the forward pass, so you can see as it's training, this is the steps it will go through, so it makes sure it's the right input shape. Otherwise, TensorFlow will yell at you. And then you just return something in the right final shape. So just the number of images you fed in times the latent size. The decoder network, which we're going to use as the other end of our pipeline, is the inverse. So it's starting with a small feature vector, and it has to get it back to the original image. So it takes a dense network that will map it to 3 by 3 by 64. And what I'll do with this is it takes the latent size, 10 units, and it maps it to a vector that's 3 times 3 times 64 long, so a really long vector. And when I do the forward pass, this will get reshaped into an image of the shape that's the number of images times a 3 by 3 individual image with 64 convolutional filters. And a filter is just a different intermediate state where it can store different important filters and features of an image. So this is a way to take a short one-dimensional vector and map it into an image domain that a convolutional neural network can act upon. The network itself will go through some upsampling techniques. So instead of doing this max pooling on the way up the decoder, we do this upsampling 2D, which is just stretching your image by a factor of 2 and doing nearest neighbor interpolation to fill in all the gaps. And in between those, it has more residual blocks. And then finally, there is a convolution that will go through all of the possible images it's created at the right resolution and compress it down to one image. So it just picks from each image, what's the most important feature? Okay, put that in that pixel. Here's my final image back that I've decoded. If you evaluate this, you can then initialize it. And if you haven't changed your runtime, by the way, you can change your runtime to a GPU, and you'll be able to run much faster. Yeah, go to runtime, change runtime type, and you should be able to select hardware accelerator. You can try TPU. I haven't tried it. For a model this big, it's unlikely to provide much. I'm sorry, for a model this small, TPU is unlikely to provide much advantage. Okay, so this is creating an encoder. I can't click. Here we go. I've set the latent size to 20. You can experiment with it if you like. If you go really small, it'll have a hard time because you have no information size to store the most important bits. If you go really big, it should train very easily. This is the decoder. And here I make one test input from the MNIST dataset. I took the first image. And then the way to go through the network is to just call the encoder on the test image, store the intermediate state, this compressed 20-long vector, and then I can decode it like that. And if you print the summary of the models, you can see that it's exactly as I claimed, residual block pooling, etc. And there's about 200,000 parameters that it's going to learn. Similarly, the decoder is also about 200,000 parameters. Because they're not mirror images of each other, they're not exactly the same number of parameters, but they're pretty similar. And if you actually look at the intermediate state, and you can plot it here, this is what it thinks it is from the encoder. It's not useful yet. And if you look at the output image, as you can see, this is a handwritten digit. And of course, it doesn't work because we haven't trained the networks yet. Okay, so how do you go about training these? I've made you hopefully believe that this will work because we have these great networks, but what's the training process looking like? So if you train a model in TensorFlow, you have to do a couple things. You do a forward pass of your models, and you get to some final result, and you compute a loss function, where you take everything and you compress it to a scalar, and you say, this is the score that the network's got. Then you have to use that score somehow to figure out what are the gradients for all of your parameters. How do I need to tweak all my parameters to get a better result next time? The way TensorFlow does that is with these optimizer classes. I'm using one called Atom Optimizer. If you're not familiar with the sort of mathematics behind gradient descent and optimizers, don't worry about it. You can look into all of that to your heart's pleasure later. Atom Optimizer is one of the state-of-the-arts that keeps track of not just what's the best way to tweak the weights, but what was the best way in the past too. So if I got a wonky image this time, I think I'm going to go a little bit this way, even though my gradients right now say go that way. So Atom Optimizer is what we'll use. And then I'm going to be plotting along the way as we train what our results look like. So I'm just setting up a lot of that plot calls here. So for the training, I'll go through the data set this many times, which is configurable. Up here, I set it to 1, you can set it to whatever. And then I shuffle the training data, which is a popular technique in training neural networks. And then I just loop through the batch of data until I've finished an epoch. So it's the same procedure as before. You get some images, you put them in the right shape, and then you go through the intermediate state and the decoder, and here's my loss function. Because I want to get the same image back as I fed in, I use a loss function that's just doing the difference between the two images. You take your input image, your output image, subtract the two, square it, and take the mean. So that's this TensorFlow mean squared error. There's other ways to train these networks. If you're doing different types of data, you might need a different loss function. But for images, this mean squared error turns out to be pretty effective. It lets you get back to your original image pretty quickly. The trainable variables are a parameter of these models in TensorFlow. So you tell your optimizer, what are my trainable variables? You can unroll your gradients by passing your loss value and your trainable variables, and your optimizer will apply them to your networks. And then the rest of this is just doing some plotting. It does it for the test data every 25 steps. And at the end of the training, it'll save the weights here. So let's run this. If you haven't run it already, hit Shift-Enter, and it should run. Don't do what I did and put a space. OK, so this should update interactively as it's training. And you can see it starts with that noise again and very quickly becomes, hopefully it's more cooperative on your computer. Very quickly becoming to look like the actual digits, even though it's only gone through the 20% of the data set so far. Has anyone been able to run this? Has anyone already finished the training before I even got to this point? All right, while this trains, let's pause for questions.
What's the benefit of max pooling?
Max pooling I used here as a way to compress the data physical dimension. There's a couple different ways you could pool down. So one of the ideas of convolutional neural networks is because you've got such a small filter going over your network, it's hard for the networks to learn big level features. So if you take a picture of your face and you want to learn, is this me or someone else, the color of your eyes matter, but also whether you're bearded or have long hair or curly hair. And so if you just have small filters, that's really hard. So the idea is you start with a big image, do small filters, and then you reduce your spatial size. And you do more small filters on the reduced size. So by the time you're deeper into your network, your individual small filters actually are covering a big region of your face. And they're starting to learn things like, OK, you've got two eyes. They're both blue in my case. Your hair is blonde and curly. No beard. You might be Corey. The way you reduce them, for me, I used max pooling. There's different techniques you could do. You could take every 2 pixels and just average them. You could do a learned filter where it's learning weights to do averaging. You could do some sort of strided pooling where you just take every other pixel and you throw out all the ones in between.
All right, so it's the compression step.
Yes, yes. Max pooling lets the network pick. This is the most important feature because it's the biggest. OK. So mine finished training. And you saw this loss curve here in blue. As it was training, this was our value for that comparison of input to output image, subtract, square, sum. This decreased dramatically. So by the time we got to the end, it was several times lower than it was when it started. And the orange curve here is on the test set. So I didn't feed those into the network during training. It has no way to know anything about those particular images, but it's still compressing and decompressing them accurately. This means that our network is generalizing. It's not just memorizing the input data, but it's actually learning okay, I know how to compress a 7, and I know how to make it look like a 7 again. And if it didn't work, you don't have time to train, you can uncomment these and load the networks that I've saved. So what can you do with autoencoders? I've talked a little bit about data compression. You could take this digit data set, use an autoencoder, compress the whole thing, and save it to disk, and save yourself, I don't know, a megabyte, maybe, because the MNIST data set is pretty small. But if you have a really big data set, and you can compress it effectively to a small size, that can save you a lot in terms of computing. You can pass that data around, you can have a smaller footprint on disk, you can gain a lot of advantages just from being able to compress your data set. And because you've done this training process, you know that the data it's compressing is valuable because it can reconstruct the images from that. So you're saving just the most important things. You can also do tasks right on your autoencoder. So neural networks are expensive. And if you want to train a classifier network or some other thing and you have to do it on a lot of images, it can be very expensive to do. One thing you could do is run an autoencoder on all of your images that's cheap and compresses it to a small size, and then run a classifier or other analysis on your compressed data. So I have an example of that here. This is a simple one-layer dense model. So it's just taking an input vector and doing a feed-forward neural network to output 10 digits or 10 units. And I'm going to use this as a classifier for MNIST. So this network only has 210 trainable parameters, and you can train it. The training steps are pretty similar, except I've used a sparse softmax cross entropy, which is the loss function Prasanna was talking about, the softmax cross entropy. This is useful for classification. And you can train this, and it should update in an epoch or two and give you good training results on the encoded data set. So you just train on your final 20 digits, and it can tell the difference between 0 and 1 and 2, etc. Autoencoders are also cool because you can take the encoded state and decode it. And you don't have to necessarily have the right intermediate state that you got from an original input image. You can start with any random number, as long as it's the right shape, feed it into your autoencoder and see what you get. So I did that here. I'm going to stop this because it's annoying to jump around. So here I took some input images. I started with them on the left, and I said, OK, encoder, what's the intermediate state? And then I asked for other images on the right side, and I said, what's the intermediate state of that? And those are just two 20-dimensional vectors, so I interpolated between the vectors. And at every step, I asked the decoder to decode it. So you can see with this example, it's smoothly transforming an 8 into a 2, or, well, a 3 into a 3. That one was easy. A 9 into a 1. And in some of them cases, the 7 turns into a 6, and it's a little bit crazy in between. And that's kind of a feature of autoencoders. You don't know, you've set no constraints on what the intermediate state could be. So it can move to anything. It can say, I'll put all the 6s way over there, all the 7s way over there, and in between is just a mystery. And there's techniques called variational autoencoders where you add a term to your loss function directly on your intermediate state to say, OK, put all of the intermediate states kind of near 0 and make them look kind of like a Gaussian distribution. And that makes this latent space in between the numbers much more easy to understand. I'm not going to cover those today, but you can search for them. And once you know the basics of autoencoders, they're pretty easy to extend to. OK, so that was autoencoders. Let's learn about GANs, Generative Adversarial Networks. But before we switch, are there any questions about autoencoders? Cool. So GANs are another way to take an input random nothing, an intermediate state, random noise, and make something intelligible out of it. They're put together with autoencoders because the networks you use are pretty similar, but you train them in an entirely different way. And this is the technique that is used to generate those fake celebrity images. The idea with a generative adversarial model is you actually train two models at once. So you start with a generator that takes in random noise, and it runs it through some convolutional neural network, and it outputs an image. And that image needs to look real. But how do you tell if it's real or not? How do you quantify that? Well, you train its adversary, a discriminator. And this network is just doing classification. You give it 2 images, maybe one real, one fake, and its job is to say, I can tell the difference. This one's real, this one's fake. So by training these together, you're able to use the adversary to computationally and quantitatively judge how well the generator is doing. If the adversary is fooled, the generator is doing well. If the adversary is perfect and knows the difference entirely, the generator is not working. And you start them training together, so they kind of learn in lockstep, and when the generator learns a new trick, the adversary has to catch up. And this training technique is why it's called an adversarial network, and it works actually surprisingly well for generating synthetic images from random noise. So we're going to train those networks here. And feel free to run through all of this. I'll move more quickly since the networks are not so different from the ones we trained before. It's not using a residual style, it's just a convolutional neural network, but it's still doing, for the discriminator, we take an MNIST-sized digit, 28 by 28, and we just do convolutions pooling, until we get down to just one answer. It outputs one final unit, which just says, it's a binary value, so true, real, 0, false is fake. It's possible I have those switched. You can check in the notes for, if one is true, real, or fake. The generator model is similar to our decoder, except instead of decoding a state that we know has all the information, we're just going to feed it random noise. We feed it garbage and hope that it can do its best. So it'll go to a 7 by 7 by 64 sized image, and again we'll reshape that, and then we'll do upsampling convolutions, and get up to a 28 by 28 sized image. So if you run this, you can initialize them. They have about 500,000 parameters in the generator. The discriminator is about half of that. And you can look at one of the first images it creates. So this is the output of the generator before you do anything. Like the decoder, it's garbage. You don't know whether that's a 7 or a 9. It's impossible. OK, so training a GAN is tricky. As you can imagine, being able to take random noise and turn it into a 3 is much harder than being able to tell the difference between a 3 and random noise. So the generator is at a big disadvantage. And we are able to train successfully because we take the adversary and we tie both its hands behind its back and put a blindfold on during training, so it has a much harder time telling the difference. And I'll show you some of those tips and tricks that I do to help the training go along. So when I compute the loss function is standard. It's a sigmoid cross entropy. It's just a binary classifier. Here we go. In the forward pass, I do a couple things. So first, I do label softening. So I've taken the output of the discriminator, which is 0 for real, 1 for fake, for example, and I soften it for the discriminator's loss function. And what that means is that I actually make 0.1 real and 0.9 fake. So the reason that's effective is because it's doing a sigmoid function, which goes from 0 at minus infinity and transitions smoothly around 0 and then goes to 1 at positive infinity. If you just let it be 0 and 1, your generator is going to predict minus infinity and plus infinity. I've got this down. I know all the answers. And it's really hard for your discriminator says that. It's really hard for the generator to beat that. But if you soften your labels and you come in a little bit, that keeps your discriminator's output values closer to 0, making it easier to trick it. It only has to be nudged a little bit in the wrong direction to trick it, instead of having to come all the way in from infinity and then to the other infinity to trick it. So we do this label softening. We also do a really nasty trick, which is label swapping. So for some fraction of the data set, 10% here, I take the real labels and I turn them to 1, assuming they were 0. And I take the fake labels, assuming they were 1, I turn them to 0. And this is just for the discriminator, so I lie. I tell the discriminator, this fake image is a real 3. Good luck. OK, so if you're still with me here, here's our training loop. This is also going to update interactively. It's a bit of a different training situation. So we go through our data, and I call this forward pass function, which is doing all of this loss function computation, label swapping, label softening, and other lying, mean, nasty tricks to help the generator do a little better against its adversary. And then when I train, I just get the different models, and I do one at a time. So I loop through the generator and the discriminator, and I say, okay, if it's the generator, I get its trainable parameters, and I calculate its gradients. I use my loss function to update, and the next time I come through, I just do the discriminator. So I train one, and then I train the other, and then I train one, and then I train the other, and they sort of leapfrog and step along. Okay, so I'm going to hit enter, and we're going to watch it train. You should be able to see it updating real and fake images if you're keeping up with this. And this behaves rather differently in a training situation than other classical neural networks. So you see the loss functions oscillate wildly. And because it's a zero-sum game, they're adversaries. They both want to win, and you want them both to not win so that they can train each other. Your loss function never goes down to very low values. It should stay at an equilibrium throughout training. And this typically oscillates a bit and then settles down. Question?
Can you explain the point of the label swapping?
Mm-hmm. So the label swapping is a way to mess up the gradient update for the weights of the discriminator. If it's always getting the right labels, even with the label softening, it's very easy for it to tell random noise and real images very early in the training. They have a fundamentally different sort of base probabilistic view. When you multiply all your weights by the real images, you got a lot of zeros. By the fake images, you got a lot of random noise. Your discriminator does really well. And it will quickly hone in its weights on the right answers. By doing label swapping, you prevent it from moving its weights and gradients in the right direction all the time. 10% of the time, you've shifted its weights in the wrong way because you lied to it. And what this effectively does is it adds noise to your gradient updates. If it wants to move this way, your label swapping tells it, okay, go a little bit that way, down your steepest descent in your gradient descent. And by this way, you slow down its training. Eventually, if you want to get a really perfect a really perfect generator, you can turn down that label swapping later in training so that the discriminator gets better, which should push your generator better. If we really cared about getting photorealistic handwritten digits, we could add in some better, more knowledgeable training steps later where we've turned down that. More questions? Yes?
So if you really compress the data a lot, in that case maybe the random data or any random data will mean some number, and in that case can the generator just be like a copy of the decoder and always produce meaningful numbers?
It can be. So it depends on what restrictions you've put on your latent space. So if you have, you really compress a lot, maybe to just two floating point numbers, and you restrict that they must always be between 0 and 1, and that they add up to 1, for example. You've put some really strong requirements on what your latent space can be. If you give those same requirements to your generator for a GAN, and you always draw two numbers between 0 and 1 that add up to 1, your generator will learn to take those and decode them to real images. So in this case, as long as you've got the right requirements on what your latent space looks like, you can interchange these. The challenge is that it can be hard to be sure that your autoencoder has done a good job getting its latent space into that right space. And a generator, from a GAN situation, doesn't care. You can feed it any random distribution, and if you train it right and you've set it all up right, it'll learn. Okay, so this has been training for a bit, and you can see that the blue is the generator loss, the orange is the discriminator loss. So even with all the tricks I played, the discriminator is doing better than the generator. But they've balanced out. After some initial fluctuations, they've basically become a zero-sum game. Neither one of them can get ahead. And the real and fake images, well, particularly the fake images, are starting to look pretty real. The real images always looked real. Question there.
Yeah, so it seems like this is kind of a chaotic process where the one network weights feed into how the other one updates. So is there a strong sensitivity to like your initial conditions in these networks somehow? If I like rerun it, will it turn out totally different?
If you rerun this, you're going to see pretty similar behavior in your loss function in this case. But these networks are a lot more fragile than just your cat-dog classifiers. If you change your activation function, if you make your training iterations different, so you use different optimizers, you use different label swapping, different softening, you're going to get different results. It doesn't always converge. One thing about GANs that nobody will tell you when you look at other tutorials online is that they don't train unless you do it just right. So the first celebrity fake paper that came out and was really famous actually took a progressive training step where they took really downsampled images. So they started at a really low resolution of real celebrities and fake ones, and they trained their GAN there. And then they used those weights and did a transfer learning to train on one resolution size up and one resolution size up, because if you just started at the fullest big high quality resolution, your GAN never trained. So there's a lot of tips and tricks that go into training these to make them work.
Is the property that you're seeing here where the discriminator is slightly outperforming the generator, is that like a general property of correctly trained GANs, or does it depend on your data and what you do?
That's a good question. I think it depends on your data. It depends on your label swapping. So remember that 10% of the discriminator's labels are always wrong, and that sets a base floor for how low its loss function can get. If you change that, you'll move this up and down. If you have different data sets and bigger models, for example, you might find that your generator can do better. If you feed it better input data, something that's closer to a real image, maybe it will outperform the discriminator. So the general location of where these two curves fall is different in each case. But the common trait is that you want them to be unable to win. Neither one wants to win. And even though the generator loss is not decreasing, the images it's producing get better.
So the hyperparameter optimization can choose a parameter, right?
Mm-hmm.
So how does it work that you have to do the hyperparameter optimization for this one?
That's a really great question. I haven't thought about that. So in principle, if you do a classification problem, you have a really easy way to quantify which network is doing better, right? You've saved some validation test set, and you can run it on those and see which one gets a better score, and that's your better network. In this case, because your loss function is changing, I don't know the answer. I don't know how you tell that the fake images that this GAN has generated are better or worse than the ones that you did on your laptop when you changed some setting. I don't know. That's a great question.
I wonder, can you explain visually why one generator or discriminator, why one has a wider range than the other?
That's another good question. I'm not sure. I do see it too, and because it's a log function, it's not linear in the loss it produces, but I don't know why this one has such a bigger, both width and, I think, bigger fluctuations.
I'm just curious about the working environment. I don't see any like CUDA code or anything like that, so does Google just handle that offloading?
TensorFlow handles that offloading. Yes, so that's why TensorFlow and PyTorch are so popular, because they've spent many, probably hundreds of thousands of programmer hours to write all their CUDA code and put it in their frameworks and give you a Python interface so that when I come along and run my GAN and say I want a GPU on the back end, it just does it. Yeah. Okay, go ahead.
When you're running the Jupyter network on your desktop or whatever, do you have that same option to say I want to use it? Or?
Typically, no. On your desktop, so you've got a Mac, I've got a Mac, we don't have the integrated GPUs, the discrete GPUs that we can use for TensorFlow. So You don't get that option here, but even if you had one of these Dell machines that has the nice NVIDIA graphics card in it, you will have to tell TensorFlow, okay, please use the GPU, not the CPU. But it is that simple. You just change a setting. I saw a question over here, I thought. Go ahead.
If the generator gets good enough, does the discriminator ever start breaking down?
In principle, no. So if the generator is perfect and it produces images that are totally indistinguishable between real and fake, the worst the generator or the discriminator is going to do is 50-50, right? It can always get to the situation where it's flipping a coin and it says, I have no idea, real, fake, 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 real, who cares?
Right, but then it's failing to discriminate.
Right, it's failing and it won't teach the generator anymore. That's the end of the scenario. Because the discriminator has no more knowledge to pass to the generator, your generator won't be able to learn anymore.
Sorry, to follow up on that, I missed the part where you would have told the discriminator that, like, for sure some are fake. Like, why would it flip a coin instead of just being like, all of these are real, and the generator be like, I'm amazing?
So you feed different images to the discriminator during training time. You always make sure to give it a batch of real and give it a batch of fake. And they have their assigned labels. So if you feed 20 images, the first 10 real, the second 10 fake, your labels are 0, 0, 0, 1, 1, 1, 1. And if the discriminator doesn't know what to do, it just flips a coin.
So the discriminator has been told, like, for sure, like, some of these will be faked, and so, like, it always has to think that.
Yes.
Okay.
And the generator's loss function goes into you take your output image, you feed it into the discriminator, and you ask, what did the discriminator say? Did it say real for everything? So the generator wants the discriminator to say real for everything because it's generating fake images, it's lying to it.
So when you're doing this, you don't tell the generator, like, just so you know, we trained the discriminator to think, even if you were perfect, like, it's not you, like, it's the discriminator. Like, you don't tell, like, does that go into the metric at all? Because isn't that perfect performance? Like, or is that just like a human thing when you read it, you're like, well, I know as the programmer that this is the case, so, like, when I interpret this plot, this is perfection.
Because we're doing this in a leapfrog method, where we train one then the other, the loss function is a little bit different each time. So when the generator's training, the discriminator is frozen. And you make your fake images, feed them to the discriminator, it outputs a probability for each one. You compare that probability to being fake for everything, and you update the generator. And it doesn't care what the discriminator was. The discriminator could have been a random number generator. The generator won't learn anything, but it doesn't care. And then when you do the discriminator, you've got a slightly different loss function because you're taking some fake images from your now frozen generator, some real images, and it gets a different loss score. So it has to make this decision real or fake. The generator doesn't even know that real images exist. Okay, I am running out of time. The rest of this notebook is just some exploration of the abilities of the GANs. You can feed in different latent spaces. So I pulled random numbers. You can do constants, all zeros, and see what the generator is outputting. You can take your encoder from before, bring it into this notebook, encode a digit, and feed that into the network if you want, and see what it gets you. And then at the bottom, there are some questions of sort of next step explorations for what you can do with GANs in terms of changing your input distribution, changing your activation size, changing your training sets. So I've left these sort of as open questions if you want to explore more. And I'm around all day to discuss as well if you have questions you want to talk about offline. I can't promise I'll know everything, but I'm happy to hear your questions. Thank you.